Good afternoon, everyone. Today, the Atom Seminar has the great pleasure of welcoming Professor Jean-Charles de Hemptinne. Professor de Hemptinne received his master's degree in chemical engineering from CU Leuven and his PhD in chemical engineering from the Massachusetts Institute of Technology. He's currently a professor at EFP School and EFP Energies Nouvelles in France. His research focuses on applied thermodynamics, molecular modeling, separation and absorption, techniques, chemical engineering and process engineering, biomass fluids, electrolytes, and more recently, hydrometallurgy. He's the author or co-author of over 100 referred publications, 3 IFP Energies Nouvelles patents, and the handbook entitled How to Select a Thermodynamic Model for Process Simulation, Problem Analysis in 3 Steps. So once again, welcome Professor Hemptinne. Thank you so much for accepting our invitation. It's a pleasure to have you here with us. Now, please feel free to start your presentation.
I decided to talk to you on a topic that I believe is very important in our thermodynamic community, which is electrolyte thermodynamics. In that topic, look at a number of difficulties that are often overlooked or not very much talked about, which are basically fundamentals, reference state, conventions, and so on, things that people don't like, but that are essential in order to understand and to consolidate, I would say, the various data types. So that's why I've put in yellow these two items in my title. This topic is something that I work with some that you mentioned here as well, Tridat Go and Saheb Maxodlo, who are colleagues at IFP EN. So as a first, how do it work? Yes, as a first slide, I have really an introductory slide just to present myself a little more. Thank you, Hugo, for the first presentation. But as we talked a bit earlier, there is sometimes a confusion between IFP Energy Nouvelle, IFP School, university. So we are not a university to start with. We are a company. Okay, we are a state company, but we are a company whose objective is to do research. And within this company, there is an IFP, there is a school which delivers masters, and we also have PhDs. But it is not a true university. Okay, so our research, the reason of our being here, I would say, of IFP, is initially we are well known for, in the previous years, for oil and gas research, and that's what we are mostly known for. But as you all are aware of, I mean, the world is turning, the things are moving, things are changing, and these days we need to move to other energy sources than oil and gas. And as a consequence, you see that this this oil and gas topic, which is still among our strategic initiatives, business units, this one is really shrinking in favor of other business units or strategic initiatives, which are renewable energy, sustainable mobility, and circular economy. And we are going really to focus on something that's more related to renewable or to circular economy. In fact, something that remains and that's always been part of IFPEN is, of course, fundamental research, and as a building block for future innovations. And that is really why I'm here, and why we are together here is for the research part. So why electrolyte thermodynamics? Well, there are two main reasons, I would say, that we are interested in electrolyte thermodynamics. One is more for the for applied reasons. Okay, this topic comes into many different types of processes that we are interested in, from biomass transformation to batteries, CO2 capture and storage, geothermal, corrosion, and you mentioned also hydrometallurgy, which is indeed the topic that we are increasingly interested in, metal purification, recycling. So it's really a fundamental place, a fundamental topic in thermodynamics. And at the other hand, we have specific challenges which we do not find in the conventional, I would say, the oil type of the molecular thermodynamics, which are, on the one hand, I would say, you see my pointer, or perhaps I should put a true pointer. This will be better, I guess.
Yes.
So you Thank you. So different types of phase equilibria. We have, well, very often when you have ions, so when you have salts in your solution, you may have several solid states. You have different liquid phenomena. You may have a vapor still, of course. So in terms of phase equilibria, you have many types of phase equilibria that may occur. So we need robust algorithms that are able to identify a stability, phase stability. Second difficulty that we encounter are the long-range ionic interactions, which means that the classical models must be revised and are no longer adapted. There are, of course, models that are specifically designed for electrolytes, but they sometimes come from another community. I will get back to that, to the chemical community, which is a bit different from the chemical engineering community, and therefore the nomenclature and the reference states at the end that they use is a bit different. So we must be able to handle all that. But in terms of the chemical engineering community, we are just in the start, I would say, of proposing new models. And at the end, and last but not least, I should say, chemical equilibria are present at the same time as phase equilibria, which means that the species that we encounter in the solutions are much more numerous than the ones that we think are present, that we've put in the solution. The species that we put in the solution, we call them apparent species, but the true species are very often much more numerous, which means that if we have parameters in our models, we end up with many more parameters, and we are in difficulty in determining these parameters. And that is really why we have started this joint industrial project, so that I would like to acknowledge here, which is a group of industrial users. You see here there are six companies with whom we are collaborating, and three software providers that we like to also thank in collaborating with us on this topic, because there is a real need of making sure that the work that we are doing responds to true industrial challenges, and that is really what we are in for. So this is about acknowledgements. Now, what we are going to talk about during this, I hope I will keep an eye on the watch, but please let me know if I'm getting late. We're going to focus on a ternary type of approach, because I think this is really one of the challenges. It's still a very simple system, but it contains in itself a number of a number of challenges, or a number of difficulties that we will encounter in true complex industrial problems. Okay, that is a system with water, a co-solvent, and a salt. And the salt, of course, is here split up into ions, a cation and an anion. And we have a solid liquid, as is shown here. So when we have this type of system, how many parameters do you think that we will have to is if you consider that we have a model that contains only binary parameters? I'm asking, but I'm replying because we don't have much time. I have lots of things to say. I've counted them. We have 10. Okay, we have 10 binary parameters only on isothermal system. Okay, we have the interactions between solvents, of course, that's one. But then with the salt, we have interaction between the solvents and the ions. We have interaction between the salt, the ion pair, I should say, and the ions. And we have this equilibrium constant, which is an additional unknown in our system. Um, so along with that, in order to set these parameters, we need data. And here again, we have also quite a lot of choices. We have VLE, osmotic coefficients, energies of transfer, speciation, but some of these we need to be able to interpret them correctly in order to use them with our model. And this is really what I'd like to talk about today, is how to reconcile these properties with our model. I will split the discussion in three pieces. One that is really related to the solvents, okay, VLE, osmotic coefficients. That means these are the properties of the volatile species. One topic that is more related to infinite dilution. I will focus on infinite dilution solutes, and then I will focus on finite dilution solute properties. Okay. So essentially, this is the summary of my presentation. We will, of course, start with really some fundamentals that I guess most of you know, but that will also help me give some nomenclature that I believe is important and that we all need to agree on. Then I will go through my three topics, and if I have time left, but I doubt about it, but we will see, I have a case study that we can discuss. So let's start. Let's start on chemical potential, fugacities, and reference states. As you all know, equilibrium is defined by the minimum of the Gibbs free energy. Okay, that's really the basic of chemical engineering of equilibrium, and for that we need to have the chemical potentials that are the tangents, I would say, of this equilibrium line, and that will come out that will result in this type of equation. When you look at phase equilibrium, the chemical potential in all phases for each compound must be equal. And when you talk about chemical equilibrium, because as I pointed out in the introduction, we will have to deal with both at the same time. The chemical equilibrium, you end up with this type of equation where nu is the stoichiometry of the reaction that may occur. We don't like so much chemical potentials. Okay, chemical potentials have a number of difficulties to work with. I mean, one of them is that it's only known for relative value; only differences are known. And more importantly, I would say, chemical potentials. The chemical potential becomes minus infinite when the concentration of a species reaches zero. And working with minus infinite is not a very convenient thing. Okay, so we prefer working with fugacities, and fugacities are related to chemical potential according to this rule here, where 1 and 2 point to different thermodynamic states. The only restriction, I would say, to this rule is that 1 and 2 must be at the same temperature. And if we do that, we can state that the phase equilibrium is written this way. And before going to chemical equilibrium, I need to write this equation here in a slightly different way, using so the chemical potential of the system that we are interested in is based on the reference chemical potential, which is equal to RT log of ratio of the fugacities, and this ratio of fugacities is often written as an activity, and this is the definition of the activity, and it's really I will really point out to what it means in future slides, because this is often overlooked and is very important to know what we're talking about. Okay, and when we do that, this equation becomes equal to this one, where we have a product of activities to the power of the stoichiometric coefficient, which is equal to a chemical equilibrium constant, which is related to the reference state chemical potentials of each species, as shown here. Okay. Now, in practice, we need to combine these, and this is done in a reactive flash algorithms, which in principle can deal with all what we're going to talk about next. Once this is said, we can focus now on the solvent properties. So solvent properties means that in my ternary diagram here, I'm going to focus on the derivatives that are along this line here. And we're going to see how they are impacted by the presence of salt. So at first, fugacities. Fugacities are convenient to work with because they are almost linear with concentration, but not quite. Okay, they are not really linear. And that's why we define an activity coefficient, because we need to have a model. And this fugacity is then described as some kind of ideality that was defined in chemical engineering. Generally, we define it as xi fi star, where xi means mole fraction. And in order to describe the non-ideality of this equation, well, we add an activity coefficient, which will bring us this linear behavior up to the true behavior. Here you have the fugacity of ethanol and water. You have an activity coefficient that is larger than 1, which essentially means that ethanol doesn't like to be in water. Okay? So you end up with activity coefficients that behave in a way that is shown here. For example, when you have ethanol-water mixture, this is typically the mixture of the solvent mixture that I'm looking at. It may be methanol or ethanol-water, and this is simple alcohols. Later on, we're going to look at higher alcohols, but that's another story. The activity coefficient is larger than 1, which means that water is more volatile when it is in ethanol than in pure water, and same thing for ethanol. So far, nothing really exciting. Everything is well known. What happens in the presence of salt? Okay, Mx is my salt here. Here I have some pictures, so some calculations that I took from PhD work in German PhD, water methanol potassium acetate, where you see the activity coefficient of methanol here on the left. The diamonds, the blue diamonds here are in pure, so without salt, in pure water, in pure solvent. So you have the behavior that I just pointed to when you have little methanol in water. This is the methanol composition. So on the right, you have pure water. On the left, you have pure methanol. When you have little methanol, you have an activity coefficient that is bigger than 1. And of course, when you go to pure methanol, you have an activity coefficient of 1. And when you add salt, you see that you are increasing the activity coefficient, which means that the methanol doesn't like. In the beginning, it didn't like to be in water, but when you add salt, the methanol really doesn't like to be in the solution, and it's going to be what we call salted out. And this is only the case when you have mostly water and little methanol. The more methanol you add, the less you will see this impact. Okay. When you look at the water activity coefficient now, pure water is here, so you have the same picture as I showed earlier. But when you add salt, you have now a decrease in the activity coefficient, which means that water is salted in. So this is something that is also well known, and for some compounds, the compounds that are generally more solvated, they are going to be salted in, and compounds that are less solvated are going to be salted out. A comment regarding the osmotic coefficient, because this is really dealing with the same property, I mean, the activity of the solvent. Here we talk about a pure solvent, but and nevertheless, this is a very often measured property, very easy to measure, in fact, where you measure the osmotic pressure when you have two connected solutions connected through some membrane that only allows permeation of the solvent, of water in this case, and you have pressure that is higher on the side where you have salts. This pressure is generally considered as being a colligative property. A colligative property is defined as a property that is independent of the type of compound involved. So it is generally written as RT times a concentration, which is the number of species divided by the volume. Okay, this is the volumetric concentration of the salt. B here is the salt. The solvent is A, and it can be written this way. That's what is often considered and therefore called as the ideal behavior. But in practice, when you do the computation, you will have to equate the fugacities, and you will find out that this pressure is equal to minus RT divided by the molar volume of the solvent times the logarithm of the activity. X gamma is the activity of the solvent. Now, the osmotic coefficient is defined as the ratio of these two pressures. And you will see, therefore, that you end up with an equation like this: logarithm of the activity of the activity of the solvent divided by nu is one in this case. Okay, it's 1 salt that I'm considering. The molality times the molar weight of the solvent. Please notice that when gamma equals 1. This does not mean automatically that phi equals 1. Okay, and this ideality that one might consider is not really the same ideality as what we consider, which is the activity coefficient. Okay, osmotic ideality is not the same as activity ideality, I say. Okay, so that's something that's not often mentioned, but I think it's worth mentioning. Now let's look at another property. Let's look at the Gibbs energies of transfer. That means properties at infinite dilution. Why? How did I come to this problem? In fact, within our GIP, we were looking at the system where we have acetic acid, which is dissociating into, as you know, protons and acetate ion. So this, if you like, is our salt, quote unquote. And this equilibrium constant of acetic acid, well, I did find a number of data that shows the equilibrium constant change with solvent composition. So that means that somehow they show the delta pKa. Okay, pK means minus log of this chemical equilibrium constant. So the delta pKa is minus the log of the equilibrium constant, chemical equilibrium constant, if in the solvents minus that in pure water. Okay, so what are we really talking about? Well, we are talking about activity. We are talking about chemical equilibrium constant, which is, as I pointed out, a product of the activities of the reaction that we are of interest. But these people, when they are doing their measurement, they are saying, well, this is approximately equal to the concentration of protons times the concentration of acetate divided by the concentration of acetic acid, which is not really what I was used to up to now. And I was wondering, what's the relationship, what's the link between all this? And for getting the true the exact thermodynamic meaning of all this, we need to really go back to the definition. Okay, activity being the ratio of fugacity divided by reference state fugacity. So we need to define what a fugacity is. Fugacity is a concentration times this reference state fugacity times activity coefficient, and we need to define what the reference state is. A thermodynamic state is fully defined from 4 items. These 4 items being the physical state, the composition, the pressure, and the temperature. And if you look at the conventional knowledge that we have in chemical engineering, I would say we have 3 types of well-known reference states. Of course, we could invent others, but the most often used one so far, at least in my previous life, I would say, was the ideal gas reference state, in which case composition is pure, pressure is generally atmospheric, And temperature, of course, temperature, it needs to be the same, needs to be the system temperature in all cases. So there's no question about the temperature. But there is a question about this other physical state, composition, and pressure. We have for solvents, generally, if you work in the liquid state, well, we consider that the reference state is a pure liquid at vapor pressure, at the temperature T. And when you talk about solutes, well, very often people talk about infinite dilution reference state. Well, this is a terminology that I really don't like, okay? Because at infinite dilution, as I said in the introduction, at infinite dilution, the chemical potential is minus infinite. So the composition is never really infinite dilution. The true definition is to say that we have a Henry constant physical state. A physical state that is defined based on this ideal fugacity behavior. That means the fugacity is proportional to the mole fraction, and the proportionality factor is the Henry constant, which is itself defined as the limit of F divided by X in the solvent. Okay, which means that we need to have a solvent. This is important to know. Okay, the pressure at which this is defined is the pressure of the solvent, and the composition is pure. That means that at the end, the reference state fugacity will be the Henry constant itself, xi equals 1. Okay, even it's an extrapolation, of course. It doesn't exist physically, or it may not exist physically, but that's the definition of the reference state fugacity. Now, this is fine. But when we look at the results of our chemists who are measuring the chemical equilibrium as a function of composition, well, they use other types of concentration units. We use mole fractions, but these people may use molality or may use molarity as a reference state. And this changes the physical state definition. And also, very not stated, but very often also the composition, okay? In such a way that in here when you're working with molality reference state, you have a molality. The fugacity, ideal state, the ideal fugacity is considered as proportional to the molality times Henry constant. And the Henry constant is defined as the limit of the ratio of fugacity divided by molality. This is not the same as the Henry constant in the mole fractions behavior, because molality, if you write it as a function of mole fraction, you will see that you have a mass, the molar mass of the solvent that appears. And if you work with the concentrations, you will see that you have a volume of the solvent that appears. Okay. If you do this, you have then the reference state that is defined, that is here. The reference state in the case of molality reference state is HIM, and the reference state, if you have in the molarity reference state, is HIC. Okay. So yes, just a reminder that I just mentioned that earlier, there is no infinite dilution reference state. Rather, use Henry's law-based reference state. I prefer that nomenclature than infinite dilution, because infinite dilution is really not. I mean, it brings people to a wrong understanding of what we're really talking about. So, as a summary, the fugacity is written this way: the reference state and the activity coefficient. For the different types of compounds. Each compound may have its own reference state. There is no problem with that. Gases are generally described with fugacity coefficients. Solvents are generally described with activity coefficients, more fraction-based activity coefficients. Solutes may be described with more fraction-based activity, asymmetric activity coefficients, so gamma IH. Which is related to the gamma I in this way, gamma I infinite being the infinite dilution activity coefficient. But chemists very often use molalities if they are kind, and if they are unkind, they use molarities I'm saying that because if they are unkind, that means that we need to know the volumes, which is often something that is not given in the problem. And the volumes of course change with temperature. They change with solution, the composition of the solvent, and as a consequence, the use of molarities is often a little more complex when we are analyzing the data, but we need to be able to work with that because many papers talk about molarities and concentration units. So the point is here you have conversions. You can convert everything into everything. There is no problem about that, as long as you have well defined what is a solute, what is a solvent, and what is the volumes of in this case, the volume of the solution. Okay, the V is the volume of the solution. Okay, let's go back to our delta pKa. Now we have gone through all this. We are able to, we know that this is the definition of the delta pKa, and we know what the chemical equilibrium constants, how they are defined, both in the pure solvent or in the mixed solvent, and in pure water. In the pure water, they are defined in this way, okay, with water reference state, and in a mixed solvent, they are defined in the same. Just replace W by S. But please notice that these chemical potentials here are not the same. Okay? And therefore, the logarithm of this ratio here is written as the sum of the differences between the chemical potential, and this will be the Gibbs energy of transfer of the ion I from the pure water to the solvent. Okay, and it can be computed from the ratio of these fugacities. And as we like fugacities we are able to compute them with our models. So we should be able to make the link between our model on the one hand side and these data on. So this is slide. Here you have the way you go about this. So this difference in chemical potential is RT of the ratio of the reference state fugacities, which is the concentration-based Henry constant in the solvent versus in water. And you can compute this using the molar volumes of the two states and the infinite dilution activity coefficients. And this, our models is able to compute. Note that these data do exist. And as a result, these data should be used in order to parameterize or to validate, depending what you're doing, the models that we are developing. Okay, and here's an application of all of this because you know that titration is something that is very often used as a basis for understanding what's happening in hydrometallurgical systems, in particular, where we have lots of ions present. And we see as a function of pH what is going to happen. So here we make sure that the acetic acid, the titration of the acetic acid, indeed yields an equivalence pKa of 4.9, which is a theoretical value that we should find. And what's happening when you add methanol? Here you see, you recognize again, 0% methanol is the pure water titration curve. But when you add methanol, 20%, 50%, 80%, then the curves are changing, and they change according. And this makes sense. I mean, you're able to using our calculation describe the actual speciation of the species. I mean, what is the concentration of the species? How is this acetate here in our context here? How is the acetate going to distribute in the different types? Acetate ion, potassium acetate, or acetic acid. Well, you see that in 0% methanol, as you expect at the equivalence point, so 4.7 approximately, you have the acetic acid that disappears and the acetate ion that appears. But when you add methanol, you add the potassium acetate, the ion pairing with potassium acetate that is going to appear, and even more so at 80%. And in addition to that, you see that the equivalence point shifts to the right. That means the pH at which this phenomenon occurs is correctly reproduced. Okay, so this is about infinite dilution properties, but now we are interested very often at finite dilution. So we need to see what happens with this ionic activity coefficients when we go to higher concentrations. And very often for this purpose, we use the MEAC, the mean ionic activity coefficient. Okay, the mean ionic activity coefficient is, well, some chemists may not agree with my way of presenting, but let's go for it and see whether there are some reactions. It's a potentiometric measurement in which you have an anode that is dipping into a solution, an anodic solution, and the cathode that is dipping into cathodic solution. Both are metals that react with the solution as shown here. I mean, at the anode, you have a reduction that forms ions with electrons. So the electrons are going to accumulate in the anode and therefore create a potential difference between the anode and the cathode. And the salt bridge in between the two is such that the cations, I mean, the ions can migrate freely between the two solutions. So at the end, what's really of importance is that you have a chemical equilibrium. Well, equilibrium, not really. Okay, that's really the key. We are not really at equilibrium here because we have a voltmeter that stops the electrons from flowing, which means that you have in fact no reaction occurring, even though there is no equilibrium. Okay, we are not at the minimum of this G as a function of chemical of psi, but we have a slope. Okay, and this slope is necessary in order to have electromotive force, which is actually what is measured. Okay, the electromotive force is directly related to the slope of the Gibbs energy, with the progress of reaction, which is the amount of electrons in the reaction of interest. Okay, and when you compare this equation with, okay, so first of all, what is the dg dxi? The dg dxi, we know how to compute. This is exactly equal to the in the very beginning. But this time it's not zero. So we should write it as we usually write it, as a sum of reference state chemical potential plus RT logarithm, the product of the activities to the power chemical the new i's, the stoichiometric coefficients. Now, when we compare this with Nernst law that all electrochemists use daily, well, then you directly see that in fact we have the E0 here. This E0 is nothing but this reference state delta G of reaction. Okay? It's a delta G of reaction in the reference state. And this Q here, well, it's the product of the activities of within the solution. The activities of the metals are one, because the metals are generally in the solid state, which means that at the end we end up with an equation that looks like this. So that's often written like this, where the activities are defined with molality reference state. I don't come back to that. Now you understand where this comes from. So that is what our colleague experimentalists who are doing potentiometric measurements, what they are measuring, which can be written as E0 minus 2RT over nu F logarithm of the molality of the salt. This molality they know what amount of salt they've put in the solution, minus the activity coefficients, and that is exactly what we're going to be interested in. Now, if you put on another equation where you put on the left-hand side everything that is known and on the right-hand side everything that is not known, then you have a function f, and you can plot this f as a function of the molality of the salt, or better as a function of the square root of the molality, because if you consider that this activity coefficient it can be written based on the Gibbs on the Baihuko limiting slope, in which case this product here is proportional to the square root of the molality. The point is that you need to extrapolate this result to zero molality, because at zero molality, you know that the potential that you're measuring equals E0. The activity coefficients are going to be 1. So at the end, the potential equals to 0. So the F function equals E0. So the extrapolation yields the value of E0. E0, which we know is in fact the reference, the Gibbs energy of reaction in the reference state. The reference state being that in the solvent that is being used. So that may be pure water, or that may be any solvent that is used in the solution. So this E0 is an information on its own, because it gives us Gibbs energies of transfer. In addition, we have the composition. When we plot the results as a function of molality, we will be able to extract the activity coefficients of the ion pair, the mean ionic activity coefficients. So as a message, this method allows us to get both the activity coefficients and the Gibbs energies of transfer. So I believe this type of measurements is very useful for our analysis and for our applications. Next, another type of property that is possibly of interest to us. Certainly of interest to us, because that's what we want to describe also, that's solid liquid, typically in liquefaction or precipitation phenomena. When you have several points on this solid liquid line, you can state that because this equilibrium, the solid liquid equilibrium it's truly a phase equilibrium, but it's often written as a chemical equilibrium, which is essentially at the end you'll end up with the same type of equation, and written with a chemical equilibrium constant that is then dependent on the reference state that is used. Again, which in other words can be said about the activities. The activities are defined as a ratio of fugacities, and here you find the reference states that are being used. So if you use reference state consequently, that means pure water reference state. In that case, this curve here, this phase boundary can be said is an isoactivity line. And if you have one point, if you have several points, you can make sure that they are all on the same. They all provide the same activity, and this is what the model can. Then we have to check whether the model works correctly along this line. If people, and that often happens, consider the activity as solvent dependent, well, in that case, you simply split this ratio into two pieces, one which is the ratio with respect to the reference state in the mixed solvent, and here you have what is generally called the ionic activity or the mean ionic activity coefficients, which is the one that is defined based on the mixed solvent reference state on the one hand, and on the other hand, you will have this ratio here, which is nothing but the Gibbs energy of transfer. Conclusion. Yes, I'm quite in time, I believe. I don't know how you feel about it, but so far I'm so good. So I have told you about 4 points, but essentially 3 of them. That first, I have given you some elements about chemical potentials, fugacities, reference states, and I insisted on the fact that data from different origins should be reconciled using our thermodynamic model, and that this is a really check to see whether the thermodynamic model is really consistent. For doing that, we went looking at solvent properties to discuss phase equilibria, osmotic coefficients. We looked at solute properties at infinite dilutions, and here I talked about Gibbs energies of transfer and I talked quite a bit about reference states. And at the end, I talked about solute properties at finite dilution. And here I talked about ionic activity coefficient from potentiometry. I also talked about solid liquid isoactivity curves. That's it. So